Hello, I'm an old guy and I do maths. Today we're going to have a look at what a cubic is. And there are a few things to cover. We'll start with the very basics. The largest power in a cubic is the third power, hence cubic. It can have squares in it, it can have constants, it can have x to the power of 1, but the highest power is x to the power of 3. And the basic shape of a cubic graph is one of these, the very basic shape. So this one would be x cubed, and this one would be negative x cubed. So odd powers in their basic form generally occupy this quadrant and this quadrant when they're positive, and when they're negative generally occupy this quadrant and this quadrant. They can move up and down, and they can certainly move into the other quadrants, there's no question of that. But if you think about positive and negative linear equations, positive ones generally drift in this direction, negatives generally drift in this direction. And so it is for negative powers. If this were x to the power of 5 and negative x to the power of 5, you would see it occupying the same sort of territory. But anyway, this is the basic shape, positive, negative. Now, we're going to move down the page and look at the type of cubic graph that you're more likely to encounter and give you an idea of the sort of equation that you would be dealing with for something like this. So, as you see, it's quite a different shape to what you saw further up the page. Much more extravagant curves on it. And instead of having just one interception point on the x-axis, it's in this case got 3. One of them is in negative territory. 2 of them are in positive territory. And that's a not uncommon feature. Okay, so normally what you'd see in textbooks is you'd see this point being named A, this one B, this one C, and you would see an equation built up with x plus A times x minus B times x minus C. I thought what I'd do instead is, just for this, because there are other graphs to look at, I'd put numbers in here and you could see how this thing really works. So I'm just going to number the x-intercepts on the x-axis. I'm not going to put coordinate points in there. Let's say that this is -2, and we'll say that this is 1 and that this is 3. Okay, so what that means is that the factors of this thing are as follows: x plus 2, x minus 1, x minus 3. Now, if I put my fingers over one of these factors, what you'll see is something quite familiar. So if you had a quadratic with interception points at 1 and 3 on the x-axis, the factors of it would in all probability be x minus 1, x minus 3. This is just one order above that. And if we expand this thing, this is what it will look like. So I'll just do the expansion here, and you can see quickly how you work up the full expansion from these 3 factors. What I'm going to do is I'm going to take these factors and create a quadratic. So that's going to be x squared minus 4x plus 3. Okay, and then I'm going to multiply that through by x plus 2. So I'm going to multiply through by x first, and I get x cubed minus 4x squared plus 3x. And then I'm going to multiply through by 2, and I get 2x squared, note that I'm working in columns, minus 8x plus 6. And then I can add those. And I've got x cubed minus 2x squared minus 5x plus 6. Sorry, I hope you can see that now. X cubed minus 2x minus 5x plus 6. And that is the equation of this cubic graph. And I've worked that up from the factors that I knew. And a point of intersection with the y-axis is 6. So I will now write these in as coordinates. And you'll see that I have, for the most part, found all the points of interest on this cubic. Right, let's move on. Now here's a drawing of a slightly different cubic. And what you see here is a positive cubic that only has 2 points of, shall we say, interaction with the x-axis. And so what we might do is we might say that this is negative 5 and that this is positive 3. And the factors of this, I won't go into this fully in this video. There will be a video in the series where I deal with a cubic that looks like this. But the factors of this will be x plus 5, x minus 3 squared. Where this cubic just touches the x-axis, we're dealing with a perfect square as one of the factors. And the y-intercept of this thing will be negative 3 squared, which is 9, times 5, which means that my drawing is vastly out of scale. This is 45. So apologies for that. It's vastly out of scale. But I just want you to see the difference between this and what we have here, where we have 3 distinct factors. And I guess going back to the beginning, where we have very, very simple cubic expressions, simply positive and negative x cubed. Okay, so other features of cubics are turning points, which you will have seen with quadratics, except that in many cases cubics have 2 of them. All of the ones that we've looked at so far, barring the first 2, have turning points. These do not have turning points. We'll come back to what these have in a minute. So the turning points, or the stationary points, are there and there. And until you learn calculus, the only other way that you would find the coordinates of these points is by guess or good luck, which may indeed be the same thing. So the turning points of a cubic are found by differentiating the cubic equation and solving the subsequent quadratic for 0, which to those of you who've done a bit of calculus will make perfect sense. To those of you who haven't, it's a treat in store, and it's not far away if you're doing this at high school. But the stationary points of a cubic are the points at which, that's badly drawn, but the idea is it's the points at which a tangent drawn on the curve would have a gradient of 0. And as I say, it's found by making the differential equal 0 and solving it. In this case, there would be 2 stationary points. And as I say, it's a subject for another video. But that's what stationary or turning points are. Okay. There's one other feature of note, and it is this. It's called an inflection point, and it's where the concavity, I think is how you pronounce it, of the graph changes. It's the point at which this shape begins to be this shape. And it's best seen in the very basic functions here. This is the point of inflection. This is the point of inflection. How it's found, again, for those of you who've done a little bit of calculus, it's found by solving the second derivative. For those of you who have not done calculus, you'll be looking at this very soon. You won't be looking at cubics generally at school without moving on to calculus at some point. It's not something to really concern yourself with how it's found at the moment. You should concern yourself with the fact that it exists. Okay, so that's a very quick run through of cubic graphs. It's not designed to startle or to overwhelm. It's just meant to give you a very basic look at how they look, how they behave, and what features they have. Thanks very much for watching. See you next time. Bye.